Hello everyone, I'm Norman Wahlberger and welcome to the Algebraic Calculus. Today's video is something of a highlight of this first course in the Algebraic Calculus because we're extending a classical result going back to Archimedes for the parabolic area formula to the much more interesting and complicated case of cubic curves. And it's a little bit of a subtle situation, but there's all kinds of really beautiful new aspects that are going to be arising. So we're really exploring new territory, opening new doors here. One of the advantages that we get by this particular approach to calculus. Very rational, very algebraic, very concrete. So the objects of interest are the Casteljau Bezier cubic curves. So these are formed with control points P0, P1, P2, and P3. And we've talked a lot about them in our course. They're fundamental building blocks for calculus. And we've seen that such a curve, say gamma, can be expressed in terms of parametrization involving, say, lambda, and some convex combination of the points P0, P1, P2, and P3 with these cubic polynomials or polynumbers, which are the Bernstein polynomials of degree 3. Now, if we substitute in here the actual coordinates of some particular set of 4 points, then we can re-express this in our more standard fashion as a polynomially parametrized curve, so that we have an x component or a first component involving alpha up to alpha cubed terms, and here are the coefficients a0, a1, a2, a3, and correspondingly the y coordinate b0 plus b1 alpha plus b2 alpha squared plus b3 alpha cubed. So that's going to be our algebraic form of the Casteljau Bezier curve, and these two things are equivalent. So having a Casteljau Bezier cubic curve or having a polynomially parametrized curve of this form, they're basically the same. We can go from one to the other. Now there's a lot of numbers here, but there are these secondary quantities that are going to play a very important role. And so let's define them. They are the delta ij. So for I and j indices between 0 and 3, let's assume that I is less than j. We'll define delta ij to be ai bj minus aj bi. So for example, a sub 2, 3 would be a2 times b3 minus a3 times b2. Okay, so that's our starting point, and now we're going to try to apply Archimedes' area formula to this situation. And so now we're going to identify a particular kind of such Casteljau Bezier cubic curve. We're going to call such a curve Archimedean precisely when this quantity delta 2, 3, which is a2 b3 minus a3 b2, is 0. So this is the critical definition here, identifying a subfamily of the family of all cubic Casteljau Bezier curves. Now, one other thing that we're going to have to mention is the point at infinity. So if we shift to projective coordinates, and I remind you that sort of involves augmenting the affine coordinates x and y with a third coordinate, and then looking at things in a scale invariant fashion, then there's a unique point at infinity on this curve, and it's 0, a3, b3. So you can think about that as what happens when the parameter, say alpha, gets large. When the parameter gets large, the alpha cubed terms dominate the other ones, and more or less the ratios of the entries are a3 to b3. And so when you actually sort of go to the limit in the projective sense, then you get that pair there together with 0 in the first coordinate. And we'll call this point I. So it turns out that this Archimedean condition, which is just nicely expressed in terms of these coefficients here, has an interpretation in terms of the nature of this point I at infinity. So the theorem is that gamma is Archimedean precisely when the point at infinity, namely I, is singular. So what does it mean to be singular, for a point to be singular on a curve? Well, here are some examples. So this point here, here's a curve, and this point here is a singular point. one way of saying that is that the tangent is not really well defined. There are two possible tangents to the curve at this particular point. This is often called a node. Here's another kind of situation that can happen. You have two branches sort of coming in at the same time. That's called a cusp. Here arguably there's a tangent, but actually it's a kind of a double tangent because it's a tangent of this branch and of this branch. So it really ought to be counted twice, so it's not really an honest tangent. And here's another kind of example of a singular point. You have an isolated point where most of the curve is over here, and then there's this one point which is off by itself. Again, here obviously there's no tangent to the curve. This theorem is saying that this Archimedean condition geometrically is equivalent to the point at infinity actually being singular. Now that does involve some discussion of projective coordinates and how we analyze points at infinity. And in the course proper, in the worked problems, we'll go over that and explain why this is and why it's true. Okay. But it's important to understand, or at least to appreciate, that this algebraic condition has a geometrical interpretation involving this point at infinity, which plays quite an important role in the story. Now here is a very different characterization of that same Archimedean property. This theorem says that gamma is Archimedean precisely when a certain condition is satisfied for the 4 points, the 4 control points of the Casteljau Bezier curve. So here's P0, P1, P2, P3. These are the control points. Our curve, gamma, something perhaps like that in red. And this curve is Archimedean precisely when the signed area of the cyclic spline P0, P1, P2, P3, in other words, this quadrilateral, oriented quadrilateral like that, if that signed area is twice the signed area of the oriented cyclic spline P0, P2, P1, P3. So the spline that we get by going like this. Okay, so if the first one is twice the second, that's exactly equivalent to it being Archimedean. Now, this is actually relatively easily checked because the condition on Archimedean is just a certain algebraic combination of coefficients being 0. And if we expand that out in the context of the 4 control points that define the curve, then this formula kind of just follows out by a little bit of rearrangement. Now there's an alternate way of thinking about this because, well, we can think about these sort of intermediate or interior triangles. So if S0 is the triangle formed by P0 and this intersection point here in P3, so that triangle there, and S1 is this signed area, and S2 is this signed area, and S3 is this signed area, all oriented in the same way, then this condition turns out to be equivalent to, perhaps the simpler condition, that S0 is equal to S1 plus 3 times S2 plus S3. Interesting that there's a 3 here. That 3 will figure in other places in this theory. Okay, so that condition is a local condition, purely in terms of the 4 control points and the shape of the quadrilateral that they form, involving the standard signed areas of cyclic splines. And that's equivalent to the Archimedean condition, which we've seen is equivalent to having a singular point at infinity. Now, if we put these two conditions together and stare at them, we see that there's an interesting consequence. Because let's say this condition is satisfied for these 4 control points. That means that the point at infinity on the curve is going to be singular. But that means that if we take any other set of control points for the same curve, any other set of control points, then that other quadrilateral will satisfy exactly the same condition because it's equivalent to the point at infinity being singular. So automatically we get as a consequence that this particular property, if it holds for one control quadrilateral, then it holds for all of them. That's quite interesting already by itself. Okay, and so now we come to Archimedes' area formula for cubics, which is in my view, a really beautiful result. And I think firmly establishes the power of the algebraic calculus. And it really is hard to argue with a theory which, after one sort of course, can discover and easily prove and come to grips with something so ultimately fundamental and powerful and interesting. And historically important, because what we're doing is we're going back to really the first computation in the history of calculus, and certainly one of the most important calculations done by Archimedes in the context of the parabola or quadratic curves, and extending that to the cubic situation. It's a very natural thing to do. And the way it works out is so beautiful that it really ought to be in every first-year calculus text. Okay, so what is this lovely theorem? Suppose that gamma is, first of all, described, written down as in our first formula, and it's an Archimedean DCB cubic curve. And that we have 2 points on it, A, which is gamma of t, and B, which is gamma of u. Then we have 2 statements. So the first is a kind of preliminary statement. The first statement is that if M is the midpoint of AB, so here's point A and point B on our curve gamma, and there's the midpoint M. Then the line IM, I is the point at infinity on this curve. So that's actually at infinity, but I'm drawing it here. And actually the curve kind of would go through here, so really we should put some blue curve going through there. But this is at infinity, so okay. Anyway, this line IM, there it is there, meets gamma at a unique point, C, there it is there, which in fact is just gamma of t plus u over 2. The curve gamma at the average of the parameter values defining A and B. Now, a cubic curve typically meets a line in 3 points. That's sort of the generic kind of thing that can happen, although other things can happen depending on the situation. But typically we expect 3 points of intersection. And so you might ask, well, why is it appearing here that there's only 2 points of intersection, this point C and this point I at infinity? The reason is because I is a singular point, and so in some sense the curve is going through there perhaps like twice. You can think about it that way, all right? So the curve is really crossing through there twice. There's 2 points of intersection of the curve at I, and this is then the 3rd point of intersection, and it's unique, and this is the formula for it. Okay, and now we come to the Archimedes area formula in this cubic context, which is that if we look at the signed slice area from t to u of this curve gamma, so that's the signed area of what we get when we take the curve together with the oriented segment from B to A. So we're going around the curve from A to B and then straight back from B to A. And it's this green area there that we're interested in. The statement is that that's 4/3 the signed area of the triangle ACB. So when we put it this way, it's exactly the same formulation as Archimedes' parabolic area formula. There also the point C could be defined in terms of the unique meet of the line through the midpoint and the point at infinity on the parabola with the curve. In that case, the point C had some additional properties which are not necessarily so applying here, at least in the naive way. But this particular property that I've emphasized in the quadratic case is the one that generalizes in the cubic situation. And remarkably, the 4/3 factor is exactly the same factor that appears in the quadratic situation. So this is very much an extension of Archimedes' parabolic area formula to cubics. All right, so let me give you the sketch of the proof so you can see the logical structure. And the details involve some computations, sometimes rather considerable computations, and we'll leave that for the online course. So details will be laid out there more fully. So let's start with the general DCB curve. Here's our form for it, gamma, in terms of A's and B's, X and Y coordinates. And we'll assume that we have A, which is gamma of t, and B, which is gamma of u. These are 2 points on the curve. Now, the line IM. I is the point at infinity that we've already talked about, and M is the midpoint of A and B. Okay, so those 2 points determine a line, and this is the equation for that line in projective coordinates. And it obviously involves t and u, but it also involves, of course, these coefficients, but it does so in a way through these delta objects. So delta 0, 3, that's the particular cross product of the A's A0, B3 and A3, B0. And here's a delta 1, 3 times t plus u over 2. And here's the delta 2, 3 times t squared plus u squared over 2. And the other coefficients are minus b3 to a3. Now, this is the general case where we're not necessarily assuming an Archimedean curve. So it's interesting to try to compute things in the general case as well. Okay, so notice that here there is a delta 2, 3 appearing. In the Archimedean case, that term will disappear. That will be important for us. In any case, in general, this thing here meets the curve gamma of v. So if you let v be a third parameter and ask when does this line meet this point, well, then you see you have a quadratic equation in v. Just sort of write down what it means to be incident, this point being incident with this line, then you get this equation here involving delta 1, 3 again, delta 2, 3, some t plus u over 2, t squared plus u squared over 2, and minus delta 1, 3 v, and minus delta 2, 3 v squared equals 0. That's a quadratic equation for v. Now, when delta 2, 3 equals 0, in other words, when we're in the Archimedean situation, then this term happily is gone. And then we have a linear equation in v, and this term here is also gone. So it becomes actually very simple. The delta 1, 3's cancel, and we immediately see that v is t plus u over 2. So in the Archimedean case, this simplifies dramatically, and there is indeed only one solution. So there'll be one point on the curve which is on this line aside from the point I at infinity. So that's the first half of the theorem that I wrote down. Okay, so now let's look at the second part of the proof, where we are starting with, let's say, a general cubic curve gamma. And here is the expression for its differential, or the area differential, d of gamma. So if gamma is the curve p comma q, then this is the quantity p dq minus q dp. That's the quantity that we have to Faulhaber integrate in order to get assigned area. So it turns out to be a reasonably pleasant expression, especially when you use these delta objects. So there's delta 0, 1 plus 2 delta 0, 2 alpha plus 3 delta 0, 3 plus delta 1, 2 times alpha squared plus 2 delta 1, 3 times alpha cubed plus delta 2, 3 times alpha to the fourth. And then we're in a position to find the signed slice area. So I remind you the signed slice area is obtained by taking the signed area of a segment and adding to it the signed area of the oriented segment coming back from the endpoint to the beginning. Okay. So we can work all of that out, and then we can simplify, and here is the formula for the signed slice area from t to u of gamma. So it's an expression times u minus t cubed, and in here is delta 1, 2 over 6 plus delta 1, 3 over 4 times t plus u plus delta 2, 3 over 10 times t squared plus 3tu plus u squared. Now, when we're in the Archimedean situation, the delta 2, 3 equals 0. Then what happens is that, first of all, we can introduce this other point c, which is gamma of t plus u over 2. And we can calculate the signed area of the triangle ACB. Because we have 3 points, we have their coefficients exactly, we can compute the signed area of that triangle. And it turns out that this is the expression that we get. There's a u minus t cubed term as before, and now multiplying that, delta 1, 2 over 8 plus 3 delta 1, 3 over 16 times t plus u. Now, how does that compare with the sine slice area in the case when delta 2, 3 equals 0? Well, when delta 2, 3 equals 0, then this quadratic part is not there. And we just have these two terms multiplying this. And when you look at these two terms and compare them with these two terms, pleasantly, there's a nice ratio. In fact, the sine slice area is exactly 4/3 the sine area of ACB. And we can see that because if we multiply this by 4/3, we'll get 1/6 there. And we multiply this by 4/3, we get 1/4, which is exactly what we have there. And otherwise, these two expressions are exactly the same. And the factor here is exactly the same. So that's a proof that given this important, this crucial condition that delta 2, 3 equals 0, so we have to have this Archimedean property around, otherwise this is not going to work. But if we do have that, then the sine slice area is exactly 4/3 the sine area of this inscribed triangle. That's exactly the same form as the classical formula of Archimedes for the slice area of a parabola. Same 4/3, same kind of triangle, same slice area. It's exactly the same. Now, there's actually quite a lot of additional really beautiful stuff that's happening in this situation, sort of around this Archimedean formula. And I especially want to show you this kind of restatement of it, where we are making contact with the Casteljau Bezier framework of having 4 control points. Okay, so we'll assume that our points A and B are the outside of these 4 control points. So P0 is A, and there's P1, and there's P2, and there's P3, which is B. So that's the segment that we've been considering up till now. And we're considering that portion of this DCB cubic curve. So the theorem now is that if gamma is Archimedean, okay, and I remind you that that condition can be expressed just in terms of areas associated to this quadrilateral formed by these 4 control points. Okay, we don't have to look at infinity. We can just look at some areas and make some relatively easy calculations to determine exactly when this condition is happening. So if we have gamma Archimedean, then we have another formula for the sine slice area of the curve. So again, the same quantity. There's the curve. There's the segment coming back. So we're talking about this green area, right? The area sliced off by this segment AB from the curve. That sine slice area is in fact 3/4 of the sine area of the cyclic quadrilateral P0, P1, P2, P3. So this quadrilateral here, you take 3/4 of its sine area and you get the sine slice area. So that means actually in practice that you don't need to find this point C. Okay, you don't need to make this line IM and see where it intersects the curve. If you want to know what the area of this slice is, then all what you need to do is calculate the area of this quadrilateral, oriented quadrilateral, and take 3/4 of it. And I also want to point out that the number 4/3 is then appearing really twice in this picture. So here's the triangle ACB. If we multiply that by 4/3, then we get the sine slice area of the curve. And if we multiply the sine slice area of the curve by 4/3, let's put that on that side, then we get the area of the big control quadrilateral. So from triangle to curve slice area is a factor of 4/3, and from the sliced sined area of the curve to the big quadrilateral is another factor of 4/3. And finally, just to suggest that there's actually more interesting stuff happening here. And in the course, there will be a wider investigation. There's actually quite a lot of additional, really fascinating things that are happening here in this situation. They will be investigated there, but I just want to end with this thing here, which shows that this point C that we were talking about, this inscribed point, can actually be obtained in a very nice way. So if n is the midpoint of P1 and P2, so m was the midpoint of this segment, and if now n is the midpoint of this segment, Okay. Then it turns out that this point C is actually on this line between n and m, and is a nice affine combination. It's 3/4 of n plus 1/4 of m. So that means it's in the ratio of 1 to 3. The segment to this segment is in 1 to 3. And so we're connecting with the convex linear combinations that we talked about earlier in the course. And because n and m are themselves just combinations of p1, p2, and p0, p3, then it's not hard to just rewrite this as an affine combination of the 4 control points of the Casteljau Bezier. And we get that the point C here is 1/8 of P0 plus 3/8 of P1 plus 3/8 of P2 plus 1/8 of P3. And of course, C is actually on this line. So this line to infinity can also be found by taking the midpoint here and the midpoint here and joining up. So this is all happening in the Archimedean case. Important to note that, right? This is not for a general cubic. It's just for the Archimedean cubics for which our Archimedean formula works. So I think this is a highlight of the course, and it's, I think, solid evidence that, yes, this algebraic calculus point of view not only clarifies a lot of things, not only provides a logical and rational and completely computationally sound approach to calculus, it also opens the doors for new discoveries and beautiful new vistas. So there's much to learn. I'm Norman Wahlberger. Thanks for listening.